And good morning, everybody. Welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 16, and then we are going to finish off Standard 17 today, with continuing our discussion on vector fields. Office hours are the usual ones for the rest of this week. Got one this afternoon from 2 to 3, and tomorrow morning at 10, and tomorrow afternoon at 1. Let me tell you about the schedule for the rest of the semester. This is our last day of talking about going through standards. On Friday, we are going to have a quiz on Standard 17, and the rest of class on Friday is going to be doing a little bit of review. So on Friday, it's going to be up to you all what we discuss. I'll be happy to answer any questions you have. I can do sort of like an overview of what were all the major things we did this semester and how did they tie together. If you want to work through some practice problems, we can do that too. It's up to you. So one of your things I've listed under homework is bring questions on Friday for things to talk about. Next Monday, it's going to be the last midterm of the semester, Exam 4, which will be over all 17 standards. And then, since Monday's our last day of class, after that, it'll just be the final. So your final exam will be on Monday, May 3rd, from 10:30 a.m. to 12:30 p.m. It'll be in here. You'll have 2 hours. It's a 2 hour. You'll have 2 hours for the final, but I'll write it to just be like the other exams. It'll be cover every standard 1 through 17. You'll just have more time than usual to work on it. If you all would like, you can take the exam with my 845 section potentially. If everybody wants to, I'm going to run out of room there. So their exam is actually going to be Friday of next week, Friday, April 30th, from 1 to 3 p.m. I think I made it during the 9 a.m. Monday, Wednesday, Friday time slot. If you all would like to take the exam with my 845 class, let me know. Send me an email, and it's likely that I can make that happen. Also giving them the opportunity to take the exam in your time slot potentially, although not much room in there for that, so we will see. But if you want, you can take the exam in the other time slot if that works better for your schedule or travel plans, etc. Just you have to send me an email ahead of time so I can okay that. Just pass back everything I had for you. I updated Blackboard yesterday as of yesterday morning. If you did some retests yesterday afternoon, that's not on Blackboard yet. But encourage you to check to make sure your mastery totals are up to date and that I'm not missing anything. Does anybody have any questions or comments before we get started for today? All right, in that case, a group of mathematicians and a group of engineers are traveling by train to go to a conference. The engineers each buy a ticket, but only one of the mathematicians buys a ticket. Of course, the engineers are all telling mathematicians, "Oh, you all are so screwed, you're going to get in so much trouble." And suddenly one of the mathematicians yells, "Hey, the conductor's coming." All the mathematicians quickly disappear into a single restroom. The conductor checks the tickets of each of the engineers and then knocks at the restroom door and says, "Ticket, please." The mathematicians slide their one ticket under the door, the conductor checks it and leaves. Then, when the coast is clear, the mathematicians all come out, and the engineers are all very impressed. After the conference, they're all going to they all take the train back home, and the engineers decide they're just as smart as the mathematicians, so the group of engineers only buys a single ticket. This time, the mathematicians don't get any tickets at all. Engineers are asking the mathematicians how they expect to get away with that, when suddenly one of the mathematicians shouts, "Hey, the conductor's coming!" The engineers all rush to the restroom, and then a few seconds later, one of the mathematicians knocks on the restroom door and says, "Ticket, please." See where it's going from there. Never try and outsmart the mathematician. And with that, it is quiz time. So, as per usual, you all know the drill. Let me know if you have any questions. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please. Okay, so in class on Monday, we had started to talk about vector fields and flow lines to vector fields, where a vector field is a function from Rn to Rn. I'll give you a second to get your packets out, I guess. We said that vector field is a function going from Rn to Rn that we can visually represent by drawing arrows, where you draw an arrow at a point where the arrow corresponds to the displacement vector you would get from plugging that point into the function. And we said that a flow line of a vector field, in essence, is a path that follows along with the arrows. In other words, it's going to be a path, x of t, going from a function going from r to rn, so something that can be represented parametrically, where the derivative of x prime of t is equal to big F of x of t. And last time we looked at we looked at a few examples of vector fields and looked at an example of finding flow lines of one of them. What I'd like to do today is to find a flow line of a particular vector field, big F of x comma y equals negative x comma y. And in particular, I want to find a flow line that happens to satisfy an initial condition that if we plugged in 0 for t, we would get the point 2 comma 1. So in other words, if we take a look at a graph, so this was the vector field we looked at last time, f of xy equals y comma negative x, had this sort of circular motion to it. We found that the flow lines look like circles of different radii about the origin. And one example was like x of t equals sine of t comma cosine of t, gave us one of these. And today, I'm going to look at this one, f of xy equals negative x comma y, where this vector field is going to have infinitely many flow lines. Any of these paths you can see when I sort of click on a point is going to be a distinct flow line. And I would like to find a flow line in particular that passes through this point 2 comma 1, where in particular at t equals 0, we get this point. So I'd like to find a formula for this flow line right here that happens to start at 2 comma 1 and then follows along with the arrows. Any questions or comments about things from last time or what we're doing with this graph before we get started with this problem? So let's take a look-see. So we want to find a flow line that happens to satisfy a certain initial condition. What we're going to end up doing is we're going to find all of the flow lines of this vector field, and then we're going to pick the specific flow line that happens to satisfy this condition right here. So, according to our definition of a flow line, we need a path. We need paths from R to R2 here. R2, since this is a vector field that takes in and spits out vectors in R2. We need to find the paths from R to R2 that happen to satisfy this condition right here. In other words, we can say that if let's say if x of t as a path from R to R2 is a flow line of this vector field, big F of xy equals negative x comma y, what we're going to need to have happen is that we need that the derivative of x of t is going to have to be equal to big F of x of t. So just like we did last time, we're going to give names to the component functions of our path. I'm going to call it little f of t and little g of t. And if little f of t, if we can say that the path x has formula, x of t equals little f of t, comma, little g of t. Little f and little g are just going to be our component functions of the flow line. What would x prime of t be equal to in this case? Rob?
Negative f of t. Wait, sorry, it would be...
If you're thinking of the other one. So what would we get if we just differentiated what you see here? Luke, would you like to help out?
f prime of t, g prime of t?
Yeah, just differentiating each of the component functions. That'll give us a vector f prime of t, comma, g prime of t. And then, Dob, I think the one you were looking at was what we would get if we were to take big F of x of t, which would be big F of little f of t, comma, little g of t. And What would that give us?
Negative f of t, comma t.
Negative f of t, comma t. Yeah, exactly. Owing to the fact that our vector field, big F, takes in a vector x comma y and spits out negative x comma y. So in other words, all our vector field really does is to make the first coordinate negative. So if we're plugging in a little f and a little g into our vector field, it's just going to spit out negative f comma g. And so we're ultimately going to be looking for functions, little f and little g, that are going to satisfy this equation right here, that little x prime, that x prime of t is equal to big F of x of t. So if x prime of t does happen to be equal to big F of x of t in this scenario, I think that's going to give us two equations of things that are going to need to be equal, if this vector is equal to that vector. How can we set up two equations of things that need to be equal in order for x prime of t to be equal to big F of x of t in this scenario? Jacob?
Okay, could we say that, like, still in, like, vectors would be f prime t, g prime t equals negative f prime t equals g prime t, so that was just f prime t equals negative f t,
Yep, f prime of t needs to be equal to negative f of t,
and then g prime t equals g of t.
and g prime of t we're going to set equal to g of t. I concur. Yeah, and this is going to be the equations that little f and little g need to satisfy in order to make our initial path x of t here a flow line of the original vector field. So what we're going to be doing is we're going to be trying to find what functions f are going to satisfy this top equation for f of t and the bottom equation for little g of t. So if f prime of t is equal to the negative of f of t, we're going to see exactly which functions are going to satisfy that. And to do that, we're going to do a little trick here, where we're going to take a page from differential equations, and I'm actually going to take this equation and divide both sides by f of t. If f prime of t over f of t is going to be equal to negative 1. Because that's something that should happen if f prime is f of t. If f prime is equal to negative f, should be able to divide both sides by f of t. And then the trick is going to be, we're going to integrate both sides of this equation with respect to the variable t. So, how would we integrate this? Well, first of all, let's see. Laurie, how would we integrate the function negative 1 with respect to t? Yeah, so on the right, we'll get negative t, and since this is an indefinite integral, we're going to need to add some constant term. I'm going to call it c2 for reasons we'll discuss. How about this left-hand integral, integrating f prime of t divided by f of t?
It looks like a natural log.
Ooh, it looks like natural log should show. Why is that?
Because it's like 1 over f of t and then f prime t is
Yeah, I would agree. It sort of feels like a natural log sort of integral. And in fact, I think if we do a quick u substitution, we can actually see natural log showing up. If we let, for instance, u be equal to f of t, which will make du equal to f prime of t dt. Then this integral right here is going to be just an integral of 1 over u du, which should come out to something like natural log of u plus a constant term. Which, if we substitute that back in, f of t back in for u, that's going to tell us that the natural log of f of t plus some constant, which I'll call c1, is going to be equal to negative t plus c2. When we integrate both sides of this equation with respect to t. And the reason why we did this is because at this point, now we have an equation that has f of t in it still, but it no longer has f prime of t. In fact, this is going to be an equation that we should be able to solve for just plain old f of t by itself, without having a pesky f prime of t term showing up. So that's kind of a common trick when solving differential equations like this is divide both sides by f of t and then integrate both sides, kind of get rid of the f prime of t term. Any questions or comments about what we've done so far in solving this equation for f of t? So, something I'm going to do now, other than give myself a little more room to work, is I'm going to go ahead and combine these two constant terms. I'm just going to move the c1 term over to the other side and just combine our two constant terms into a single constant term. Because constant plus or minus a constant is still just going to be a constant. And when I do that, I can get that natural log of f of t is going to be equal to t plus some combination of these constant terms, which I'm going to call c hat. Dr. Gerskell, why does that c have a hat over it? Because it's cold outside. Did you see it's snowing? Also, we've got a reason for that. Yeah, Jacob?
Does the negative of the t go somewhere?
Yeah, it goes right here. Clearly. What, you didn't see that? Clearly, Dr. Gerskell missed that. So, yeah, good catch. Should still be in negative t plus c. Yeah. So now we have natural log of f of t by itself. What's something that we can do to both sides of this equation that'll give us just an f of t term by itself? Luke?
Both sides.
Yeah, we could do the inverse of taking the natural log to both sides. What is the inverse of taking the natural log? Jackson?
Raising e to the side.
Bingo! We're going to take e to the power of both sides, since e to the t and natural log of t, or e to the f of t and natural log of f of t are going to cancel each other out here. And what we'll get is the f of t on the left-hand side by itself has to be equal to e to the negative t plus c hat. And here, we can break this apart and write this with exponent rules. Write this as e to the negative t times e to the c hat. And since e is a constant and c hat is a constant term raised to the power of a constant term is still another constant. I'm just going to write that constant as a big C out in front and get c times e to the negative t. And my claim is f of t equals c e to the negative t is going to be the set of all functions whose derivative is equal to the negative of the original function. Any function f where f prime is equal to negative f of t has to look like this. Some constant times e to the negative t. We can actually check that. If we were to take the derivative of this, we would in fact get negative c e to the negative t, which would be the negative of what we started with. So in order for f of t to satisfy this first equation that Jacob, you came up with, f f of t has to be a constant multiple of e to the negative t power. Any questions or comments about that? Let's do the same thing now with g of t to see what happens. Because we're also going to need that g prime of t is equal to g of t. So it would behoove us, that's a funny word, behoove. It would be good for us to find which functions g are going to be equal to their own derivative. So how would we find that? How could we? What would be a similar way that we could start off to what we did with f of t to find all functions g such that g prime of t and g of t are going to be equal to each other? Dom, any ideas?
Do the same division to create a differential equation.
Okay, so that'll give us g prime of t divided by g of t is equal to 1. And if we integrate both sides with respect to t, on the left-hand side, we're just going to get natural log of g of t plus c. I mean, that there it's going to be the same as with the f, so I'm not going to do the substitution again. There's natural log of g of t plus some constant term, c1. Lindsay, what would we get on the right-hand side when we integrate 1 with respect to t?
Plus
Yeah, we're going to get just t plus some other constant term. And just like before, going to combine the constant terms to get natural log of g of t is going to be t plus some c hat, let's say. And what can we do to both sides to get g of t by itself now? Gary, any ideas?
We raised the both sides.
Yep. And so what we'll be left with on the left is e to the natural log of g of t. E to the natural log cancel each other out, so we'll just have g of t is e to the t plus c hat, which just like before we can rewrite as e to the t times e to the c hat and get c e to the t power for our g of t term. So in other words, any function that's equal to its own derivative is going to have to be a constant multiple of e to the t. And we can check this very quickly. If we differentiate with respect to t, nothing's going to change. We would get the same thing, c e to the t again. Any questions or comments? So, in order for x prime of t to be equal to f of x of t, so in order to have a flow line, we need these two equations to be satisfied. In order for the first equation to be satisfied, we needed that f of t is a constant multiple of e to the negative t. In order for our second equation to be satisfied, we need that g of t is a constant multiple of just plain old e to the t. So what can we say about all of the flow lines of this vector field then? I think we can say that any flow line of f of xy equals negative xy is going to have a formula of x of t is equal to what? If we kind of combine what we have so far, where keep in mind we said x of t is we defined to be little f of t comma little g of t. If we plug in the functions we found, Katie, what's that going to give us?
C times e to the negative t, c times
Everybody okay with that? That?
Should we differentiate between the C's?
Very good. I was wondering if someone was going to catch that. Yeah, technically, we can't use the same constant term necessarily, because we don't necessarily need that the constant term in f of t has to be the same constant term as in g of t. They could be different constant terms. Because we just need any constant multiple of e to the negative t, comma, any constant multiple of e to the t. So Jack, I think I agree with you there. We need to label our two constant terms differently to account for the fact that they don't have to be the same constant out in front. So any flow line has to look like this. And the fact that there's infinitely many flow lines to our vector field, which we saw in kind of looking at the graph on the screen earlier, the fact that there are infinitely many flow lines is going to correspond to the fact that there's infinitely many choices for C and D, our constant term, in our vector field. So by picking different values for C and or D, we can get different flow lines. So we're not quite done yet, though, because the problem didn't ask us to find all the flow lines. It asked us to find a single flow line in particular. Specifically, the flow line that happens to satisfy that x of 0 is equal to 2, 1. So what can we do if we wanted to find that flow line in particular? Yeah?
Plug in 0 for t, and then set each of the component functions equal to 2, 1.
Okay. So in other words, treat this like sort of an initial value problem in Calc 1 and say, well, plug in 0 to this expression, we'll get something in terms of C and D, and then we can just set that equal to 2, 1 and solve for C and D. I like it. So if we do that, we'll get that x of 0 is going to be C e to the negative 0, comma d e to the 0, which should be equal to 2, 1. C e to the negative o, negative 0. Other than looking like a corrupt CEO, what is that expression going to evaluate to what?
That's just 1.
Yes, e to the 0 is just 1. So this will be C. De to the 0 is similarly just going to be d times 1. And so that'll be equal to 2, 1. And let's see, Hannah. If we set C times 1, comma D times 1 to be equal to 2, 1, what is that going to tell us about C and D respectively? Exactly. C is going to be 2, and D is going to be 1. So then, I think for our final answer, we're going to have a single vector field, or not a single vector field, a single flow line to our vector field that is a flow line, meaning it looks like this, and it also happens to pass through the point that satisfies x of 0 equals 2, 1. What are we going to get for our final answer then for x of t? I like it. Yeah, we just plug in the values that Hannah found, C equals 2 and D equals 1, into our general form for the general formula for the flow lines, and that's going to give us the specific flow line, x of t equals 2e to the negative t, comma, e to the t. That's going to be a function that happens to satisfy its derivative is equal to f of that function. And if you plugged in 0 for t, you would get the point 2, 1. And if you actually graph that out, 2e to the negative t, comma, e to the t. One of these days I'll figure you out, screen. we should be able to actually see that, here, go away. If we graph on top of this vector field, the curve x of t equals 2e to the negative t, y of t, that's not right, 2e to the negative t, not negative 0 times t. And y of t is e to the t, and z of t, I'm just going to set equal to 0. Constant primary color, so it's easier to see. We do, in fact, get a flow line that happens to follow along with all the arrows of the vector field and kind of going up and to the left here. And at t equals 0, it does pass through the point 2, 1. So this did, in fact, give us the flow line that we were looking for. If I click on the point 2, 1 to find flow line passing through this point, it's going to match up with this parametric curve I just graphed perfectly. Or what if I could click exactly at the point 2, 1 at least? So any questions or comments about what we just did? So this is definitely something I would call a tricky problem. In that, in order to solve this, we had a few different steps that we had to do. We had to start by saying if x of t equals little f of t, comma little g of t, in order to get this equation to hold, we had to find that little f prime had to be equal to negative f, g prime had to be equal to g. We then used a method from differential equations to find what did all the f of t's and g of t's look like that solved this. In this case, if f prime was equal to negative f, then we found f had to be some constant multiple of e to the negative t. And similarly, if g of t is equal to its own derivative, we found g of t had to be a constant multiple of e to the t. This gave us a general formula for what our flow lines of this vector field are going to look like. Ce to the negative t, de to the t. As Jack pointed out, we had to give a new name to one of our constants because these constants did not have to be the same. And finally, using what Hannah and Alex did, they they plugged in x of 0, I think at Brianna's suggestion, to solve for what C and D look like for the particular flow line we were looking for, the one that satisfied the condition, and in doing so, found a single flow line that happened to, first of all, be a flow line of our vector field, and that satisfied when you plugged in 0 for t, we got the point 2, 1. Any questions or comments? Yeah, Kate?
So I guess this is just because it's going from R to R2, so it's actually in three-dimensional space. How
How would you graph this?
How did we see that t equals 0 on the actual vector? Just
Oh, pull this back up for a second. How did we know which point corresponded to t equals 0? That's the way CalcPlot 3D works, is if you click at a point, it'll find the flow line where t equals 0 is at that point.
so how does okay.
So how can you tell just from looking at this if you didn't have that point?
Yes, like what does it mean that t equals 0?
So that just means that happens to be a single value of t that you plug in and get this specific point. If you were to plug in every single real number as possible values of t, it would trace out all the points on this curve. I think for positive t, it'll give us points going kind of towards the direction of the arrows going this way, and negative t, you'll head in the opposite direction of the arrows.
You have a three-dimensional graph. Can you show that?
Yeah. So this is sort of what's going on here with technically arrows should be going out in infinitely many directions, this way, that way, and that way. Here, CalcPlot 3D likes making things in 3D, but really everything's happening in 2 dimensions. since our vector field was a function from R2 to R2, the graph of our vector field is really just a graph in R2 with arrows. If we had a vector field from R3 to R3 and did this sort of problem, then we would have a three-dimensional graph to look at. But really, everything's just going to be taking place in the xy plane in this example because our vector field just goes from R2 to R2. And so our path is going to be a path from function from R1 to R2. And that's why everything appears two-dimensional in this example. You could, with a little more work, similarly do an example from R3 to R3. And I think there's actually a practice problem in the packet that does that. I like our two examples because A, they're a little bit quicker, and B, they're much easier, I think, to sort of visualize what's going on with something like this.
So if instead of saying x of 0 equals 2, 1, if we had said, for instance, x of 1 equals 2, 1, we would have gotten completely different equations, and then C and D would have been completely different numbers, different constants.
So, well, let's look at that for a second. So you're saying if we kept the same thing, but just made this difference right here?
Right.
I think we wouldn't have gotten completely different equations. We still would have gotten to this point because we didn't. To get up to here, we never used the initial condition at all. The only difference would have been here in solving for C and D. We would have gotten different constant values for C and D. We would have got something like C over E is equal to 2, so C is equal to 2E. And D times E is equal to 1, so D is 1 over E. And that would just change these constant multiples here. But it would still be the same set of flow lines. It would just give us a different flow line for the same vector field.
Right, so even though the constants are different, your curve there will be the same. The flow line will be the same. Because you'd be starting at
Yes, it would actually give the same flow line. It would just the equation would look different.
since it's parametric.
Yep, that's parametric in a nutshell. It's going to trace out the same curve, whether at t we want to have this point at t equals 0 or at t equals 1. Good question. Well, I'm glad you asked. I chose to give an example where x of 0 equals 2, 1 because plugging in 0 for t made it the easiest to solve for C and D. Whereas plugging in something like 1 is a little bit more algebra involved, but not too much harder. All right, so that's everything I wanted to do with flow lines. Last thing I wanted to talk about is going to be the notion of a conservative vector field or a gradient field. Let's spend a few minutes and talking about that. Unfortunately, we're not going to have as much time to talk about conservative vector fields as I would like. Originally, the last 2 standards of the semester were all going to be looking at these things. So instead of kind of getting to talk too much about their properties, I want to define what they are and kind of how do we determine whether a vector field or not is conservative, other than by, I don't know, giving it some sort of political pull. So, in general, we're going to say that a gradient field, or a conservative vector field, is just going to be a vector field, F, something going from Rn to Rn, such that big F is equal to the gradient of some function f, or some function little f, going from Rn to R. So in other words, a vector field is considered to be a gradient field if we can find a function little f whose gradient is that vector field. And if this happens, we're going to say that little f is a potential function for big F. So let's take a look at an example of finding one of these, looking at a gradient field and finding what would its potential function look like. In other words, given a vector field, how can we find some function from Rn to R whose gradient is equal to that function? So, in particular, I want to look at the vector field x comma y comma z is equal to 2xy comma x squared plus 1 comma cosine of z plus z. So this is going to be a vector field going from R3 to R3, and our goal is going to be to find some function little f going from R3 to R such that the gradient of little f is equal to this big F, is equal to this vector field. So 2xy comma x squared plus 1 comma cosine of z plus z. So let's see what does that mean? If the gradient of little f is equal to this specific vector field, this thing going from R3 to R3 with 3 component functions, what's going to be the relationship between little f and each of these pieces? Specifically, what expression related to little f is going to have to be equal to 2xy here? If the gradient of f has its first component equal to 2xy. Luke?
Del f over del x.
Bingo! The partial derivative of f with respect to x. Using the fact that the gradient of a function little f like this is by definition just the vector made up of all of its partial derivatives. Del f del x, del f del y, del f del z. So we need to find the function little f where del f del x is 2xy, del f del y is going to be equal to x squared plus 1, and finally, del f del z is going to be equal to cosine of z plus z. So let's see if we can do that. Find a function little f from R3 to R with all of these specific partial derivatives. Emily, if we know del f del x is equal to 2xy, what information is that going to tell us about little f? Integral with respect to what? Yeah. We could say that if del f del x is this thing, then f has to be an antiderivative of this with respect to x. I can get behind that. So what would we get if we took if we integrated 2xy with respect to x? Jackson? We're going to get x squared y x squared y plus some function in terms of y's and z's. And this is a little bit sneaky. Dr. Gerstle, why aren't we just getting a plus c? It's because we have lots of variables involved. And so if we wanted to find functions whose derivative with respect to x is x squared y, we could have something like f equals, or 2xy, excuse me. We could have f of x equals x squared y plus 2. That would have a del f del x of 2xy. We could also have, though, something like x squared y plus 2 cosine z plus y cubed. That would also be an expression where if we differentiated with respect to x, we would get 2xy in the same way. Because we differentiate z terms and y terms with respect to x, well, that derivative is just going to be 0. And so, if all that we know is del f del x is 2xy, we know that f has to have an x squared y term, but it could potentially have a bunch of other terms with y's and z's showing up in it as well. So that's why we can't just throw in a plus c, because we could have the other variables other than x showing up. All that we know from f about this is that the only term in f that has an x in it is going to be x squared times y. So we can also use the fact that del f del y is x squared plus 1 to tell us that f of xyz is going to be an antiderivative of x squared plus 1 with respect to y this time. Olivia, what would we get if we integrated x squared plus 1 with respect to y?
X squared y plus 1.
X squared?
Plus, do we have to use a different variable g?
Yeah, because it's not necessarily going to be the same function or use the same variables in the function. Let's call it h.
Plus h of x comma z.
Yeah, plus some function that has x's and z's potentially in it, just no y's. Because similar to what happened there, if del f del y is x squared plus 1, all that tells us is that the only terms in f that are going to have y's in it are going to be an x squared y and a y plus a y term. We could also have some other terms with x's and z's in it that if we differentiated with respect to y, would just go to 0 and still give us x squared plus 1. And finally, we did the same thing with del f del z. We could get f of xyz has to be an antiderivative of cosine of z plus z taken with respect to z. And Avery, what would that give us? Give us a sine of z plus a 1/2 z squared, or z squared over 2. What did you call it? U? Sure, you can call it U. Plus some function in terms of x that has potentially x's and y's in it. Because if we differentiate something with just x's and y's with respect to z, that's going to go to 0 and not affect the partial derivative of f with respect to z. All right, Brianna, can you think of a single function f that can be equal to all 3 of these things?
X squared.
Hold on just a second. Let me finish this.
X squared y plus y plus sine of z plus 1/2 z squared plus maybe a constant.
Yeah, we could have any constant term we want, and if we had a plus c at the end, that wouldn't affect any of our partial derivatives. But I think I like your answer, Brianna, because I think that'll do it. Because this function is a function that is equal to x squared y plus terms that only have y's and z's in them. In other words, x squared y is the only term with an x in it. If we differentiate with respect to x, we just get 2xy. It's also the case that if we differentiated with respect to y, we'd get x squared plus 1, meaning this function has a form where the only y terms in it are an x squared y term and a y term. And finally, the only terms with z's showing up in them are going to be the sine of z plus 1/2 z squared term. So this thing is going to have all the partial derivatives that it needs to have in order to have the gradient of this function equal to our original vector field. Del f del x is 2xy, del f del y is x squared plus 1, del f del z is cosine of z plus z. So this is going to give us all of the potential functions of big F of x, y, z. Quick question. Brianna, why not? I'll pick on you some more. How would this have affected your answer? If, let's say, del f del y, or if f had to have this form instead of just what it had previously.
Well, you couldn't have it as two separate, like you couldn't have x squared y plus 2x squared y, so it wouldn't really work. I can't think of a way that it would make sense because that specific part would need to be present in both the integral del f del x and the integral del f del y.
I would agree. In this case, if f had to have both this form and that form, there's not a single f that could make that happen. Whose only x term is x squared y, but also has a term of 2x squared y showing up in it. So in that case, I would just say our original vector field is not a gradient field because it doesn't have any potential functions. There's no way to find something whose gradient would be the original vector field if that was the case. So not all vector fields are gradient fields. Some are, some aren't. This one was because I chose an example that worked out, but if you can't find a single function, little f, that satisfies all the conditions you need it to, you would just say the original vector field is not a gradient field. And I give you an example in the packet of one of those. Dr. Nursel, where did the name conservative vector field come from? The reason why conservative vector field is sometimes used to talk about this sort of vector field is this sort of vector field conserves work being done when you do a special type of integral along a vector field. That's going to be the last two standards. Basically, if you do an integral around the loop inside of a conservative vector field, then the total work that will be done is 0. There's some nice physics-y applications to that. That's it for the last standard of the semester. Don't forget, on Friday, I'm going to give you all the opportunity to ask review questions. So bring questions to class on Friday, and I will see you all there. Sorry to have to rush a little bit towards the end today. Sorry to pick on you a lot towards the end, everyone. You're usually pretty good at giving me fairly quick answers, though, and that's new. Since we're running out of time, I thought I'd call on you again.
Have a good day, Mr. Dr.
You too. Actually, I have a question. No. It's not the same as adding all of them necessarily, because if we had added all of them together, we would have had to have had 2 copies of x squared y. But the reason why we don't want that is because if we have 2x squared y, then f doesn't have this form anymore. Instead, what we want to have happen is we want to find a function little f that can look like all 3 of these simultaneously, which isn't necessarily the same as adding them all together. The reason why we only had a single x squared y term, for instance, is because this tells us the only term that can have an x in it is an x squared y term. This told us the only terms that can have a y in them is a single plus y, and as well as an x squared y term. And so x squared y is only going to show up once because that's what our conditions told us. If this was just an x squared,
So we have x squared
actually, this would be another scenario where it doesn't work out in the end. There is no potential function because this would tell us the only x term we can have. We have to have an x squared term, and that's the only term we can have that has an x in it. But this condition would tell us we also have to have an x squared times y term, and it's impossible for that to happen. To have an x squared term, but no other x terms, and we also happen to have an x squared y term. That couldn't happen. So that would be another scenario where we would just say there is no potential function. There is no little f that can satisfy both this condition and that condition at the same time. Does that make sense? Cool. Yeah, good question. But I had a couple minutes. I was actually going to ask that to the class, like, should we have 2x squared y terms? And the answer turned out to be no. Oops, I should end class.